In this session, we shall concentrate on time domain representation of continuous time linear time invariant systems. So, we shall represent the continuous time linear time invariant systems by means of convolution integral, and we are going to concentrate on how to derive this expression of convolution integral and the procedure to evaluate this convolution integral to obtain the response of the system. So, we have already seen that every signal can be expressed in terms of a impulse function. So, we may write the signal in terms of an impulse function as x of t is equal to integration from minus infinity to plus infinity x of tau delta of t minus tau d tau. Now, let us assume we operate on the input x of t with the operator h to result in the output y of t, which mathematically can be expressed as y of t is equal to x of t operated with the operator h. Now, what this y of t is? It is the response of the system. Output y of t to the applied input x of t is called as the response of the system. Then the impulse response h of t of the system is output due to the input delta of t. So, for if you are suppose operating with some operator on the input and obtaining output y of t, and if the input is replaced with delta of t, then whatever the response you obtain, that is called as the impulse response. Similarly, the step response denoted by s of t is the output obtained by the input, that is step input u of t. So, response of the system is output due to input x of t, impulse response is the output due to impulse input, and step response is the output due to step input. We are concentrating on output y of t due to input x of t, and we seen that every x of t is expressed in terms of shifted impulse and can be expressed as y of t is equal to integration minus infinity to plus infinity x of tau delta of t minus tau d tau operated with the operator h to result in this output y of t. Now, given that the system is linear time invariant system. Now, if the system is obeying the linearity principle, then this operator has to operate on this product term and generate the same output y of t. So, assuming that the system is obeying the principle of superposition, we shall write this expression as y of t is equal to integration minus infinity to plus infinity operator h on x of tau delta of t minus tau on this product signal d tau. Now, our observation is x of tau denotes the amplitude of x of t at instant tau, and it is a single amplitude of x of t at tau. So, the operator that we are operating it on a signal which is variable in t, and therefore, we operate this on this delta of t minus tau in the expression. So, y of t is equal to integration from minus infinity to plus infinity x of tau delta of t minus tau operated with the operator h, and then the integration with d tau. So, now the system is a time invariant system. Now, time invariant system, what it obeys? Output is independent of the time variable, and therefore, every shifted input generates the shifted output. So, here it is a shifted impulse. So, shifted impulse should generate a shifted impulse response. So, if I replace this h of delta of t minus tau with the shifted impulse response here, what is the shifted impulse response? So, if you replace this with the shifted impulse response, you get this resultant expression for y of t. So, what is the shifted impulse response? The shifted impulse response is denoted by h of t minus tau, where when you operate with the operator h on delta of t, you obtain the impulse response h of t, and if you shift this impulse response h of t with tau, you get this shifted impulse response. So, replacing with this h of delta of t minus tau with h of t minus tau, we get the convolution integral expression, that is y of t is equal to integration from minus infinity to plus infinity x of tau into h of t minus tau d tau. And this mathematically can be represented with the operator, convolution operator, as x of t convolved with h of t, and by convolution integral expression as integration from minus infinity to plus infinity x of tau into h of t minus tau d tau. Now, to understand the procedure to evaluate this convolution integral expression, we need to obtain y at the instant t. Now, consider that we are obtaining the output y of t at the instant t is equal to 0. So, replacing t in the previous expression with 0, we get y0 is equal to integration from minus infinity to plus infinity x of tau into h of minus tau d tau. Now, what is this h of minus tau? It is a reflected signal h of t, and obtained with that h of minus t and t replaced by tau. So, very important is x of t and h of t to be sketched with respect to the variable tau and reflect h of tau and obtain h of minus tau, obtain the product signal x of tau and h of minus tau, and then integrate the evaluation of this product term from minus infinity to plus infinity to obtain y at t is equal to 0. This is what is required to do if we want to evaluate this convolution for one instant at t is equal to 0. So, we need to identify all such values of t for which y of t obtain the finite value, and we have to repeat this procedure for all such finite values. Consider that we need to find out t at minus 1, then we need to obtain h of minus 1 minus tau and this product signal, and then we need to integrate this product signal. Now, to obtain h of minus 1 minus tau, we have to shift left h of minus tau by one amount. H of minus tau we have to shift left by an amount of 1, and for t is equal to 1, we need to obtain the product x of tau into h of 1 minus tau and integrate the product signal, where h of 1 minus tau can be obtained by shifting h of minus tau to right side by one amount. In this way, in general, if you want to obtain h of t minus tau, if t is positive, we have to shift right the signal h of minus tau by an amount of t, and for negative value of t, we have to shift left h of minus tau. So, to begin with, we have to start with the largest value of t towards the negative axis. To find the largest value of y of t towards the negative axis, use this expression: left end of y of t is equal to left end of x of t plus left end of h of t, and the right end of y of t is equal to right end of x of t plus right end of h of t. Once if you obtain the left end and right end, then you have to evaluate the convolution integral between this bounded value. So, in this bounded value, you can divide the bounded value in between various regions and integrate the expression. For every value of t, we have to obtain the product sequence x of tau into h of t minus tau, and not add, we have to integrate this product signal. This is what we need to do while evaluating the convolution integral. So, thank you students.